now what we're going to talk about is something called resonance, where some compounds can have multiple different correct Lewis structures. And so resonance structures, by definition, are that. They are Lewis structures, so they are Lewis structures with the same skeleton formula, so the same layout of elements. So with same skeleton formula, but different electron arrangements. And so one example of this is ozone, O3, where if we look at the number of electrons we have, each oxygen gives up 6 electrons. We have 3 of those, so that gives us 18 total electrons. So we can draw up that. We have 3 oxygens. We'll just put them in a row. We can form single bonds between each of the oxygens. And so that would be 4 electrons used on single bonds. So I'll just say 1 bonds. And then we can put lone pairs around our exterior oxygen. So I'll do that in green. So we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we'd use 12 electrons on oxygen lone pairs. And that leaves us with, we've used 16, so we have one final set of electrons that we can put onto our central oxygen. So 2 electrons onto central O. And if we look at that point, we see that our central oxygen, so we go E, central O has 6 electrons. And so we can go over and draw little circles around each of these guys. So this oxygen has 8, 6 from lone pairs, 2 from that bond. This oxygen has 8, 6 from lone pairs, 2 from that bond. And then your center oxygen, which we'll do in blue, that only has 2 electrons from its lone pairs and then 4 electrons from those bonds. And so what can happen is we can have each of the exterior oxygens give up one of its sets of electrons to make a double bond. So what we need is one double bond. And so we can have the case where the oxygen on the left makes that double bond. So it takes these electrons and it goes like this. So we get this structure here. So oxygen, double bound to oxygen, single bound to oxygen, put our lone pairs around everything. Or we can have the other oxygen do the same thing. So we can have this set of electrons go over here. And when I draw that arrow, I'm circling the electrons, and then they're going to form a bond there. So that would give us oxygen, oxygen, oxygen like this, where these are just the same way to put an equivalent structure. And so I'll draw an arrow between these two with a double head to say that these are just 2 equivalent ways to describe the molecule. And obviously, they're just mirror images of each other. But it's saying that sometimes the oxygen on the left is donating, sometimes the oxygen on the right is donating. And that's how we represent these separate resonance structures. The true Lewis structure that describes ozone is actually a combination of the resonance structures. So we call that a resonance hybrid. And so what that means is that we take each of our structures above. So I'm not going to draw in the lone pairs. Yeah, I'll do it. So we take our structure where we have double bonding with the oxygen on the left. We take our structure where we have double bonding with the oxygen on the right. And we're just going to bring those two together. So we're going to take these, bring them together. We'll get a purple structure that looks like this, where you have your center oxygen. In all cases, we have a single bond between each of our oxygens. But I'm going to draw these little dotted lines to say that sometimes there's a double bond. And so what I've done here is I've spread electrons, equally across all of the oxygens. And that's something called delocalization. So delocalization is equal to the spread of electrons. So spread of electrons. And what that does is it increases stability. So this increases stability. And what this is, we call this thing, this purple thing right here, the hybrid or the resonance hybrid. And it is the average of all resonance structures. And it's also, so this is the average of resonance structures. And it's what we'll say is the true structure. So we'll call this the true structure. And so you can think of this, I think your textbook talks about making a mule, which is like a donkey and a horse. You can also think of this as when we take, dog breeds and we take a German Shepherd and I guess this lab, when you bring them together, you get an intermediate between the two. And so I like my fun example of this when I think about resonance and, forming hybrids is that of Corgi mixes. These hybrids are just, Corgis in disguise, where you take the form of one of the things, like a Dalmatian in this case, you blend it with a Corgi, and it's a mix of the two. And, you need both parts to describe the Corgi. It's not just like the Corgi mix. It's not just one, not just always a Corgi. Well, it's not sometimes a Corgi, sometimes a lab. It's a blend of the two. And so these are just a couple cute Corgi mixes. We have a Dalmatian, a German Shepherd. I think that's a Retriever, a Pug, a Lab, a Husky, a Rottweiler, and then I can't remember what this one. Maybe this one is. Maybe a Heeler. And so when we look at these resonance hybrids, we can loop back to that bond order, which we said that bond order is effectively the number of bonds that exist between two different things. And so, excuse me, in the case of our resonance hybrids, we'll say that the bond order, because it's this average, the bond order is typically going to be fractional. So typically fractional. So let me just respell that. Typically fractional. Because of averaging. And so remember that, bond order is calculated by looking at bond type, where a single bond has a bond order of 1, double is 2, and triple is 3. And so if we look at something like NO3-, which has from nitrogen 5 electrons times 1, so that's 5. From oxygen, each oxygen gives 6, so we have 3. Well, we have 3 of those, so that's 18. And then from our charge, we have a minus charge, so that gives us 1 more. So that's 6 plus 18, so that's 24 total electrons. We can draw up our structure here. So we have nitrogen flanked by 3 oxygens. We can form our single bonds, 1, 2, 3. That uses up 6 electrons on single bonds. Then we can put lone pairs around our electronegative atoms. We'll do that in green. And so we have at this point 18 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we use 18 electrons on oxygen lone pairs. And at this point, all of our oxygens have an octet, but our nitrogen does not. And so we have 3 different ways to give that nitrogen 8 total electrons. It can get electrons by forming a double bond with this oxygen. We'll call that number 1. It can use it by getting electrons from this oxygen. We'll call that number 2. Or from a double bond with this oxygen, we'll call that number 3. And so we can draw up each of those different structures, and we'll use that double-headed arrow to denote each of their equivalent forms. So we have our nitrogen, oxygen, 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 and we'll double bond here for number 1. And then I'll put that in brackets. And that is equivalent to number 2, which is nitrogen, oxygen, 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 double bond here, which is equivalent to this one right here, nitrogen, oxygen, 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 with a double bond here. And if we take all of those and we average them together, what we get is this structure right here. So nitrogen always forms a double bond with each of the oxygens. and then sometimes it has a double bond with each one of them. And then we'll just take each of these, and I put them in brackets because we have that minus charge from that nitrate. So each of these has a minus charge. And then I can put in the lone pairs on each one of these. So in this case, we put 3 sets of lone pairs if it's single bound, and then only 2 sets if it's a double bond. And in order to calculate bond order for these, we're going to look at, in each of these structures, we'll pick one of the nitrogen-oxygen bonds. So we'll look at this one. And so in order to calculate that bond order for the true structure, which is, the structure that we have above, we're going to look at how many bonds that nitrogen forms with oxygen in each different case. And so we'll call that bond order, I'll just say BO, is equal to, in structure 1, that nitrogen and oxygen form a single bond. In structure 2, they form a single bond. And in structure 3, they form a double bond. And so since I looked at 3 different structures, I'm going to divide this by 3 to look at the average bond order across all 3. That's 4/3, which is equal to 1.3 repeated. So that means that there's always a single bond between each of the nitrogens and oxygens, and there's a partial 1/3 bond because 1 in 3 of the resonance structures show a double bond there. And so what we'll say is that these bonds in our resonance hybrids are typically going to be shorter and stronger than the single bonds, but they're going to be weaker than double bonds because they sit, between the single and double bond. And so what we're going to talk about next is how we can rank these correct resonance structures. So looking less at these correct Lewis structures. So resonance are describing things that have the same skeletal structure with the different bonding, where we're moving one electron at a time. There's also different ways that we can represent Lewis structures that have, instead of equivalent, double bonds, everything gets a chance. We can look at cases where there's a more unequal level of bonding going on. And so we'll talk about that with this thing called formal charge that we use to rank the validity of different Lewis structures.